Hi, welcome to the Calculus 2 lecture series. And this is a unit number 4, sequence and series. And this is the second video of the lecture number 23, representation of the function as a power series. Okay, let's go ahead, go to our lecture notes and let's continue what we start off, okay? So this is the, let's take a look at my lecture notes here. Okay, when we start this, we said for this section, we have 3 goals we want to achieve, right? So first one is obtain the power series. That's by manipulate a known series. And the one we did from our previous video is how do we manipulate a geometric series to become a power series. And then the second topic in this part 1 here is we're going to take a look at how do I take the differentiation and integration of a power series. And the reason why we want to do this is to try to prepare us for the the next part number 2 here. How do I do the power series expansion by differentiation and integration? So that will be our video 3. So this video 2 is basically to try to prepare the concept and the tools for our next videos here. Okay, let's go ahead, take a look here. Okay, so differentiation and the integration of the power series. Okay, so let's see what that means here. So if I know f of x, if it's some type of the power series, right? So it's a summation and from 0 to infinity, Cn x minus a to the nth powers here. And this one here has an interval, had the interval of convergences with radius r greater than 0. Okay, then also we know, right, f is continuous in these intervals here, continuous in the a minus r and the a plus r. Okay, now if this is a continuous function, then we know for all the x in this interval, right? And f may be differentiate, maybe take a derivative. Maybe so f may be differentiated term by term. Okay, so what I can do here, so is f prime x is equal to summation and from 1 to infinity. You just like you take the derivative, right? So you use the power rule, so it's n Cn x minus a to the n minus 1 here. Okay, and so in here, one thing be very careful here is instead of starting with n equal to 0, the derivative here, I need to start with n equal to 1. The reason why is because when you take the derivative, you have n minus 1s, right? So if you still keep in the 0, and then what happens, this will be negative 1 terms here. Also, when n is equal to 0, when you take a derivative, is it's zeros here. So that's why I can start with n equal to 1. Be very careful here. Okay, and okay, so then the next thing here is okay, so for all the, so same things here for all the x in this interval, a minus r, a plus r. Okay, then we may be integrated. So we say f may be integrated term by term. So in the integrating the term by term, so if I want to integrate the f of x dx, so this one here will be equal to, you just integrate your power series, right? So it will be summation n from 0 to infinity. So you just use the power rule. So this is n plus 1 Cn, then this is x minus a to the n plus 1, then plus c, right? So that's what is we talk about is you can integrate or you can differentiate by turn inside the power series here. Okay, so here the other things is the important points here, right? Okay, so the important point. Okay, so we know the both f prime x and integration f of x dx here. They have the radius of convergences here r, but the endpoints a minus r and a plus r must be checked. Okay, so because like for the first video, we said we manipulate the geometric. That's why we just say the absolute value of x less than 1. But in here, this is just a general power, the power series, right? So we, like we take the derivative, we take the integration within this interval of convergences here, but in here, one thing in here very important. So we know they have the radius of convergences r, but at the end point, right? Because you remember, like in the previous, we said the video, in the section lecture number 22, when we talk about the power series, we say, hey, we want to check the interval of the convergences here. You have to check the endpoint, right? So that's why the endpoint have to be checked to determine the interval of convergences here. Right, so in here, they just say in here, we said here, see here, like if you take a look, so we said f of x is in here, like let's tell us here, let's say, hey, we have the interval convergences here with radius greater than r. Right? So that's why we all have this radius. So we put it in this parenthesis, open parenthesis interval. But if one time we decide the interval of convergences here, you have to check the endpoints here. All right, so this is a very, very important part, right? So the endpoint has to be checked in order to get the correct interval of convergences here. Okay, so let's take a look at a couple examples here. So for this ones here, right? So we say to find the derivative. So okay, so this one's here is good. So we said the f prime. Okay, so the f prime axis here will be just the derivative of inside the functions here, right? So this is 2n, then you times the n, x minus 1 to the what? To the n minus 1s here, right? Okay, so that is pretty straightforward. Okay, so of course, if you want to find the interval of the convergences here, then you need to use the ratio comparison, right? So in here, you will say the an plus 1 over an less than 1, then you check the end points. All right. So if you want to find the interval of the convergences here. So it's kind of back to our section 11.a, when we first define the power series, how do you find the interval of the convergence? And then you need to use the ratio test and then check the endpoint here. Okay. So in here, the problem did not ask us because basically we just want to learn the skill. We already learned how to find the interval of the convergences from the previous lectures here. Okay, so now let's take a look here. They said find the f of x, the integration. So then this one is the same thing. The integration f of x dx is just be equal to, here is summation n from, let me see the here, did I, oh, okay, here, I need to be careful here, right? So like in here, I should put a f prime, be careful here, right? So it's equal to what? Start equal to 1 here, right? Okay, so now in here, the integration is from 0 to infinity. You're just integrating x minus 3 to the n factorial dx here. And then you can use the powers rule. So this is a summation n from 0 to infinity. So the powers rule would just be n plus 1. You still have this n factorial there. Then you have x minus 3, the n plus 1. Okay, and don't forget, this is indefinite integration, so you need to plus 6 here. Okay, now in here, the last ones here, they tell us if I have a power series, it's xn to the 4, xn and over 4 to the nth power, is continuous at 2 or not. All right, so the answer here is yes, it is a continuous at 2. It's because the convergence is here is what? The interval convergence is -4 and 4, right? Because this is a geometric function, so we can say x over 4 is less than 1. So that means the x is less than 4, so that's why it's 4 and -4. That means this is the domain, and if this is the domain and the x is what? X equal to 2 is continuous because this is polynomials. Right? All right, that's it. And this is the part 1 of the lecture number 23. And in the next video, we're going to take a look how do we use this integration and the differentiation skill try to help us to find the power series representations here. Okay, nice talk to you and looking forward to talk to you our next videos here. Okay, bye.